review for parallel session 6, which is characterization and exploration of small bodies. His talk is the mission asteroids, science and exploration in the space age.
Thank you, Greg. Well, it's very nice to be here, and thank you all for being here with me, and thank you, the organizers, for giving me this opportunity to speak to you. It's about 18 months, 2 years since Jen Helderman asked me to be a part of her survey node, and I was very pleased to be asked and very happy to agree. And it got me thinking about science and exploration, and immediately thought of my favorite books, or some of my favorite books from my library at home. And I think what these books represent is exploration on just about every continent on Earth, North America, Siberia, South America, Australasia, and the oceans of the world. And you read these books, you look at these explorers, and you just realize what an absolute wealth of science came out of these voyages of exploration. So it is really a privilege and a great joy to be part of an organization that is blending science and exploration. So that got me thinking. Jen said, think about asteroids. Well, the last few years of my career, I've been doing something along those lines. I've been thinking about conditions on asteroid surfaces, flying on the Vomit Comet, and so on, having great fun, doing some spectroscopy. So I thought, as these thoughts were rolling around in my head, I thought, I know what will be fun. I will write a review paper on what we've learned from missions to asteroids. You know, a couple of weekends' work, you know, and I'll have another paper. 18 months later, and it's been submitted to a journal. It's gone to Space Science Reviews. I had some absolutely wonderful reviews back from the journal. Wonderful, not in the sense that they said, this is brilliant, don't touch it, but wonderful in the sense that we love what you're doing and here are some cool ideas. So I appreciated that process. So I thought what would be fun for today is not to give you a sort of a thoroughly technical summary of what I did last week, but rather just to sort of float around with this topic and just sort of share it with you a little bit. So let's see if I'm going to tell you. I don't think I'm going to tell you anything you haven't heard already, but I hope that I've just strung it together in a way that might just give us a few minutes of amusement. So this is essentially, I had the talk prepared. It looked like it would last about an hour. So last night I did the unholy thing of going through and cutting slides. So I've got it whittled down to this. I'll give you a little bit of a review of a few things. I'll shoot through that as quickly as I can. Then what I want to do is just let my thoughts roam and expose you to some ideas that came through my mind while I was doing this job, and then talk a little bit about what I think we should do next. Now, what I stress is this, I don't know how many people have worked on this topic, how many science teams this represents, but it's a big number, right? So this is very much my personal perspective, and I hope you'll forgive me if these are not consensus ideas, but my ideas, and maybe there's somebody in the room who's going to disagree with every word I say, but that'll be part of the fun. Okay, beginning with the missions themselves. 8 missions, 12 asteroids. So what interests me as you look down this list is you can read into this list the history of missions to asteroids, what I'm trying to say, and you can also see policy evolution as you go down this list. You can see that we started out with spacecraft that were going to more important places and just dropping off at asteroids on the way. Then we started getting dedicated missions, and now we have amazing missions that are actually going into orbit around not just 1 but 2. I'm going to call Vesta and Series asteroids, and forgive me. So we have spacecraft actually orbiting. So most of these are flybys. We have an orbiter here. We have Dawn orbiting 2 here, and we have the touch and go that Hayabusa performed. So that is the history of the missions in a nutshell. The history of the discoverers is equally informative if you're interested in the history of our subject. I tried to locate portraits of all the astronomers who had discovered the mission asteroids, the asteroids that we've been to with missions. Was not totally successful, but I did find these. And again, as you read up on these individual astronomers, it's great fun. It's very interesting. You can see the history of planetary astronomy unfolding in front of you. You can see the telescopic work of the early 19th century. You can see introduction of photography, you can see the introduction of more elaborate telescopes, you can see the introduction of digital astronomy. So you can see the history of our field in this subject. Taken a couple of pictures from the Dawn team, enormous variety of sizes of asteroids that we've been to. You sit through these sessions and you hear talk after talk after talk, and you hear this asteroid and this asteroid and this asteroid. And I know for myself, for one, it's easy to lose sight of the fact that this is an enormously varied bunch of objects. This is phenomenal. You have essentially planets. You have essentially Series and Vesta, these huge objects that behave in many senses like planets. You have Iorikawa, which is basically a boulder. So you go all the way from a real planetary object with all sorts of internal mechanisms, probably, differentiation and so on, to these pieces of fragments of bigger rocks that are just flying around out there in space. And they're all going to have very different histories and very different properties, and I think we need to keep in mind as we're looking at these things just the scale, 500 meters to 958 kilometers, the scale of the range of sizes of these things. I think probably the most exciting thing, or an exciting thing, that these asteroids now, by virtue of the exploration of the solar system, are no longer points of light. They are actual real geographical places. And we can make maps, and we can assign names, and we can have great fun doing that. The IAU has come up with a way of doing this with some sort of order. That Gaspra, the craters are all named after spa towns. Matilda, it's coal fields. Ida, it's caves. It's really neat to look into this stuff. Eros is lovers. There you go. That's my favorite. And then space centers, gems, Roman cities, and apparently there's plenty of Vestal virgins for Vesta. I didn't know about Vestal virgins before we went to Vesta. So. And just again, part of my introduction, part of my overview, we have spectroscopy. So we can see that we have not just an enormous variety of sizes, we have an enormous variety of compositions. So we have S asteroids, one that's a Q, very chondritic-like. We have Vesta, which has also been, sorry, that's Braille. We have Braille that has been called a Vestoid, but it's also been called Q by different astronomers. We have Vesta itself, of course, and then we have MEX. So this is Lutetia, which is flummoxed everybody, and various groups have called it M, E, and an X. So there's one ambiguity of spectroscopy. So let me get down to, so that's by way of introduction. In the review that's about 100 pages, there's a whole lot more of that kind of summary material. But I just want to, in my 15 minutes or so, just capture some of the flavor of what I've been doing. These are some of the questions that I came up with as I was going through this. In fact, I think there's a list of about 10 or 12, but I just picked out a few here. What was confirmed by the missions? What was new? How abundant is water inside the snowline? I really enjoyed the talk that we've just heard, talking about all these cold traps and talking about the possibility of volatiles and water in particular existing for long periods of time in the appropriate environment. So I think that's something I want to come back to. And then I'd like to spend quite a bit of time talking about how we're doing on linking meteorites with asteroids. So what was confirmed? I was sat in my office in 1996 putting together meteorites and planetary science, and I was looking for a picture for the cover, and then Clark Chapman sent me the first picture of Gaspra before it went public. And I never forget that moment, that asteroids are points of light, right? And then we get this picture of Gaspra, and there it is in all its glory. It's a rock, a big rock, and it's cratered, and it's got all these textural variations around the craters. Turns out to be a big ejector blanket around the biggest crater, things like that. So this object that we'd read about for so long and sort of hypothesized about for so long became a real object. But I think we have to say that despite the thrill of getting that first picture, I don't think anybody was really surprised that it's a dry, heavily cratered surface. And a somewhat ancient surface. We can now do the crater distributions, we can assign an age to that surface, and we can see that 200 million years is young, and a billion, some of these are a billion. So we can see that these are, by and large, these are pretty ancient cratered surfaces, so I don't think that was new, so that was confirmed. Similarly, I don't think anybody was surprised, especially since we had astronomical light curves and so on, that basically the asteroids tend to be irregular fragmentary shapes, so that was not a surprise. I think that this bifurcated shape was sort of a surprise and sort of not a surprise, because I think at about the same time we started getting spacecraft going to asteroids, we got radar images. And so I think from the radar images we knew that a lot of these things were bifurcated or were contact binaries. And of course I think we pretty much knew that the bigger guys would be spherical. So I don't think the shape was a surprise. But I think what was new was the fact that a surprisingly large number of these asteroids, including the very small ones, had very thick regoliths. And I remember back in 1979, 1980, throughout the 80s, there was a conviction among a lot of astronomers that you could not have regoliths on on these asteroids. They put a limit at small was 10 kilometers, which we now think of as being quite large. But 10 kilometers and below could not possibly have a regolith because of the microgravity conditions. And so we expected to see barren rock. Well, in fact, we've seen the opposite. We've seen thick regoliths everywhere we've looked. And in fact, it's now become a bit of a science studying the mechanics, the geology of regoliths, how they move, how they flow, how they're created, difference between an ejector blanket and a regolith and things like that. So I think probably one of the most important messages to come out of the exploration of the asteroids has been the fact that regolith is everywhere. Regolith is so abundant. And of course, that has important implications, as we've just been hearing from Paul's talk, about the thermal history of the object. It also affects cratering mechanisms because a regolith absorbs energy far more readily than a rock does. So the cratering mechanics are different. And of course, it very much affects operations. Trying to do exploration in this highly dusty environment is itself a challenge. What was new, if you go through the literature as I have, this sort of very systematic way, asteroid by asteroid, phenomenon by phenomenon, what kind of struck me was how often we saw grooves on these asteroids. This is a catena which is thought to represent a fracture through the asteroid, and then regolith has sort of sunk through that fracture in a pitted way, like you see in many situations. But again, the sort of inference was these were global structures. These were weaknesses in the entire asteroid, not just surface features. The polar regio region of Ida, fractures, asteroid-wide fractures that had been opened up, in that case, by an impact crater. Rahi dorsum on Eris, it cuts the asteroid in half. It seems to go right through the asteroid, and it manifests itself on the surface. It's slightly tougher material, presumably, manifests itself on the surface as this structure. And then, as I've just mentioned, the catena on Styes is thought to represent. Now, this made a big impression on me because when looking at these surface structures, features, and reading the texture that was coming from the geomorphologists who were really studying these things, it was telling us these were coherent asteroids. Now, on the other hand, I haven't seen in these descriptions of surface features on asteroids anything that says that's a rubble pile. Oh no.
Sorry.
No. He said, I only have 2 minutes, Helson. Life is not fair. All right. The Eris ponds, at about the time we discovered the Eris ponds, maybe shortly after, we were doing experiments in our lab where we were trying to measure the evaporation rate of water on Mars. And so we put ice under a layer of regolith and we watched how quickly the water evaporated. And we did some measurements, we published some papers, but what really stunned us was that we reproduced in the lab these Eris ponds, these fine-grained deposits at the bottom of shallows. So I haven't got time now because he's on my case, but the bottom line is we think there are fluids underneath here that evaporated out, and Maybe they made the crater, maybe the crater made it possible for them to reach the surface. But anyway, the bottom line is that that pond is a fluidization feature. So we're kind of getting drawn to the idea that maybe there's water underneath the surface of Eris. It's not a bone dry. So when Paul talks about his subsurface and quotes the literature data about stability of ice, then that kind of resonates with me. And there's discussions in the literature about where the snow line is. And we have all these dozen or more, that's more than a dozen, isn't it, asteroids that show activity. So, and this is their orbit, the perihelion and the aphelion. And a lot of them are spending a significant amount of time inside the snow line. How they got there, I don't know, whether they were brought in from the outside. But it's telling me, at any rate, we have asteroids on the inside of the snow line that are active and are giving away water. Then, of course, Sears is degassing from the work of the Herschel spacecraft, observations of the Herschel spacecraft. And that actually spends most of its time inside the snow line. It brushes it off the aphelion. So we think, at least in my mind, the idea is promoted that maybe we should think about water inside asteroids, inside the snow line. Now I wanted to get to my big topic. All right, do we link meteorites with asteroids? Here is the data for the HEDs being linked. I'm sorry, this is Iorikawa being linked with the LL chondrites from spectroscopy. Iorikawa is here, which is kind of near the field where mineralogically you'd expect the ordinary chondrites. We got samples back. They were not bulk samples. They were 50 micron grains. We put those grains through the sort of analysis we can do only on Earth. And mineral chemistry puts them in the LLs. Oxygen isotope puts them in the LLs. I haven't got time to explain the plot, but puts them in the LLs. I think that's a done deal. Okay, we know that Iorikawa is an LL-type asteroid. We don't know that the LL chondrites come from Iorikawa, but we know that there's a very strong linkage there. Vesta, I think we're in a similar position. Again, I haven't got time to go through all the arguments. You probably know most of them. The fact that it's mineralogically consistent with the HEDs having some sort of affinity is not overly convincing to me, because I think there are a lot of basaltic-like type rocks out there in the asteroid belt. But what really won me over here was the data from the Dawn probe. We have carbonaceous material which has lowered the albedo and brought water. And it's a little known fact about the meteorites, the HED meteorites, that they contain water. This is the HOH corner of the diagram. And they contain carbonaceous clasts. That's been known. Both of these have been known for decades. So it strikes me that a surprising discovery on Vesta was consistent with a long-known, little-known fact about the meteorites. And so, for me, that's a done deal. Okay? And then I've got to shut up, right? Okay. For the ordinary, for Eros, I'm going to say we don't know. If you want a detailed explanation of that, you're going to have to catch me some other time. So that's my talk. Well, there's just what next. Just getting to the chase, I think number one priority, as far as I can see, is return sample, and I think the work with Iorikawa demonstrated the value of that. I think we should look for water in about asteroids, inside the snow line. And of course, the big question here, which underlies a lot of what I've been saying about rubble pile versus monolith, is what are these things like inside? So I think we should put a high priority on trying to do some geophysical studies that will get inside these asteroids. Thank you very much for your attention. I needed another 15 minutes.
I feel very guilty. Yeah, you
bad guy.
Yeah. I know what I wanted to offer to this group, and I'd like a show of hands on this. I don't know how you possibly could have condensed 100 pages into 15 minutes, and I'd like to make this suggestion. This might be a nice topic for a survey director's seminar online. Who would be interested in seeing a longer version of this? That's enough. Okay, well, we will do it. I will.
I'm flattered. Thank you.
Absolutely. So we really don't have time for questions.